Okay, so sketching a direction field in this quadrant, just as an example, you can do it in any quadrant. Okay, what's going to happen? Your direction field gets infinitely steep here. Okay, the slopes all approach infinity. Okay, so by the time you get to the y-axis, just right next to the y-axis, you just have these. Okay, so you can never get across the y-axis. So, for example, if you follow this curve, slope might do something like this, but it's going to approach infinite steepness here, okay? It's never going to cross the y-axis, right? So, slope approaches infinity as t approaches 0. So your solution curve can't cross the t-axis, okay? Now to see what the actual shape of this thing is, we'd have to have a more detailed direction field. But that's the way it's going to work out, okay? There might be some subtle details, maybe for some specific starting points, maybe you could. But in this case, I don't think you can. Okay? Now this is related to the fact that y prime plus y over t is not defined if t equals 0. One thing you might have to think about here is what happens in the limit as y approaches 0 at the same rate t does. Okay? In other words, what happens if you approach 0 along a straight line with slope -1? Okay?
You're still going to have a discontinuity, aren't you?
I'm sorry?
You'll have a...
Yeah, well, yeah, you'd have this line here and this line here, right?
Yeah.
And you would have solutions that make sense along that line. Okay? You have solutions that make sense along any other line. Okay? Now the whole point is, yeah, maybe this thing behaves in such a way that eventually you approach that line and you can have a continuous solution that crosses 0. Okay? And that solution curve, the y function, when divided by t, doesn't end up with a singularity. Okay? Doesn't end up with an undefined. Okay? But also, involves an integral 1 over t, natural log of the absolute value of t, and that's undefined if t equals 0. Okay? Maybe you can patch that, and maybe you can't. This is a particularly simple equation. Okay? And we're not going to go any deeper into that. The test for whether you have solutions is simply your system or your equation or your system of equations has to be defined for the whole interval. If there's any point in an interval where your equation or system of equations is not defined, you can't guarantee a solution. You can't guarantee the existence of a solution. Obviously, you can't guarantee that you can solve any given equation in closed form. Okay? Doesn't mean there isn't a solution, just means you can't find it, you can't express it in terms of basic functions. Okay? Or even in terms of really weird functions. Okay, there are all kinds of equations. You easily write down equations all day that nobody's ever going to solve. But they are known to have solutions. We just can't find them. Okay? But this tells you that if the equation or any equation in a system is undefined, anywhere on an interval, you don't have a solution on that interval. So you essentially split the t-axis up into intervals on which you are guaranteed solutions. Like you are guaranteed a solution on this interval because it doesn't cross zero. So anywhere to the left here, you have solutions. Anywhere to the right, you have solutions. They don't necessarily articulate in a way that gives you a patchable, continuous solution for the whole plane.